A very warm welcome to all of you. I wanted to present to you this course by describing one of the more fun aspects of what we're going to be doing throughout the semester. This is the model I've asked you to buy, and this model is one of my favorite models on the market because it is so inexpensive, yet it has so much detail in it. So let's start by looking at the model so that you have an understanding of what you're looking at when you start breaking this model into pieces. So the model starts with the medulla. We know that because immediately we see these cranial nerves, which tells you that this is supposed to present the medulla with the cranial nerves coming out of it, and the cranium will be around the whole model. Now, immediately as you go up the medulla, you'll see the two pyramids that we're going to describe at some point in our course. Immediately above that, you see the pons. If you turn the model around to look at it from its back, you immediately go up to the cerebellum. Now, above the cerebellum and right above the pons is a very small area called the midbrain. And we're going to look at the midbrain after we take the whole cerebrum off. But if you take apart the cerebellum, you can now observe the brainstem. The brainstem includes the medulla and the pons and the midbrain. So this is the brainstem. It looks like a stem of a flower. Now let's take a look at the cerebral cortex. When it comes to the cerebral cortex, there are two features that are striking. The first are the hills, and the second are the valleys. The hills are called gyri, singular gyrus, and the valleys are called sulci, singular sulcus. Now, there are two major valleys in the brain. The first one is the one that divides the two hemispheres. This is the interhemispheric fissure. Now, the other one is one that divides the temporal lobe and part of the occipital lobe from the parietal and frontal lobe. And this is called the lateral fissure. Now, in addition to these two major fissures, or large sulci, there's a central sulcus that goes all the way from the top here to almost somewhere at the bottom here, where it hits the lateral fissure. This sulcus, the central sulcus, separates the frontal lobe from the parietal lobe. Very important sulcus. And in this case, the model depicts the frontal lobe with the color brown and identifies the parietal lobe with the color blue. So approximately here is where you see the central sulcus. Now, what's really interesting about the model is that it is quite representative of a true cerebral cortex. In the cerebral cortex, you'll see an inferior region of the temporal lobe, a middle region of the temporal lobe, and a superior region of the temporal lobe. And you practically can see that on this model. There is also an inferior region of the frontal lobe, a middle region, and a superior region, less easily depicted here. You can see the parietal lobe in blue, and the parietal lobe is responsible for somatosensation. So immediately behind the central sulcus is the primary somatosensory cortex. And that primary somatosensory cortex is responsible for all physical sensations from your body. Now, behind it is the parietal association cortex, or the parietal lobule, many names to these regions, and we're going to learn a few of them. And behind that, you start getting into the occipital lobe. Now, there's a green area here that saddles mainly the temporal lobe, but part of the parietal. Now, technically, this is supposed to be Wernicke's area, but the primary auditory cortex is purely in the temporal lobe. It is part of the Wernicke's area, but the real region is in the temporal lobe. Now, when it comes to the frontal lobe, you're going to see the primary motor cortex, which is somewhere around here. And if you turn the model to look at it from the bottom, you're going to see the orbitofrontal and ventromedial prefrontal cortex. So the orbitofrontal is at the level of the orbits of the eyes. So they're around here. And then in the middle, medially, is the ventral, because it's at the bottom towards the stomach, and ventromedial, middle, prefrontal, because this whole region is prefrontal, cortex, orbitofrontal cortex and ventromedial prefrontal cortex. Now, if you look again and pay close attention, this is the prefrontal cortex, and part of the prefrontal cortex that is essential for our understanding of behavior is the dorsolateral prefrontal cortex, which is around here, sort of anterior to that brown area on the model. So I'm going to repeat again, dorsomedial prefrontal cortex on both sides, ventromedial prefrontal cortex right here in the middle, and orbitofrontal cortex. Primary motor cortex, and then primary somatosensory cortex, primary auditory cortex, and then if you turn the brain and look at its back, you will see the primary visual cortex, which must be around here. There is a fissure called the Calcrine fissure that the primary visual cortex straddles, which I could estimate it's either here or maybe this is meant to be the Calcrine fissure. It's a bit unclear. Now you're going to see something really interesting. In the model, the ventricles are presented in a translucent way to indicate that they are practically fluid-filled. It's a very ingenious way of representing the ventricles, and we'll see the ventricles in detail in a few seconds. But the ventricles are very important because they help us identify brain regions quite easily, because both in specimens, we could easily see the ventricles because they're empty spaces, and in MRIs, because they contrast a lot, fluid contrasts a lot from tissue, and therefore they make it easy to see what regions are around them. Now, the model, again, is fascinating because it shows you what we call the cerebellar peduncles right here. You see, I think this might represent, these two holes these areas represent the middle cerebellar peduncles. There are superior, middle, and inferior cerebellar peduncles, but you cannot see the inferior and superior, but you do see the middle cerebellar peduncles. Peduncles mean feet. So the cerebellum has 3 feet on each side, connecting it to the pons. Now let's take the model apart to see further what other components of the model represent actual areas of the brain. Now, the cerebral cortex is hundreds of areas that perform different functions, and they're hard to identify specifically on the model because, first of all, not every brain is exactly the same, so the model has to be an average of different brains. And because this is a small model, they might not have represented the cortices perfectly. Now let's take out the prefrontal cortex, or what's supposed to be the prefrontal cortex. And immediately you see that this model shows you the cortex in pink, and then underneath it are these white stripes. This is the white matter and the gray matter. The gray matter is presented in pink in the model, and the white matter is the striped white lines that go from the cortex down to subcortical regions. That's, again, a really amazingly good depiction of how the brain is connected. You've got gray matter on the outside, which is your cortex, connected to deep gray matter, which we'll describe in a second, with axons that constitute the white matter. Now, let's take a look at the brain from a coronal perspective. And immediately you notice that there are translucent ventricles showing up. And behind them, what looks like cortex too. This is the insular cortex. It's deep inside, and it's again being represented in such a fascinating way in this model. This is the insular cortex. This is the temporal lobe. These are the temporal lobes. And you can see the cortex with the deep white matter. Now, next to the insular cortex are underneath the insular cortex are different subcortical gray matter regions. And we're going to look at them after we remove the top part of this model. So when you remove the top part, you're basically removing the rest of the frontal lobe, as well as the parietal and the top of the occipital lobe. And what you'll notice is you've got the corpus callosum, which is represented by this. This is really half the corpus callosum. They had to cut it here. Otherwise, it's just too cumbersome to be able to put it back all together. So this represents the corpus callosum. The back of it goes like this. And then underneath it, you're going to see the ventricles. These are the lateral ventricles. And they are so superiorly placed in this model. It's quite impressive. If you remove the whole brainstem and the insula, as well as the ventricles and everything underneath it, we're going to put this aside for a second. And what you see is, again, just an outstanding representation of the hippocampus, potentially the amygdala. The amygdala would be somewhere above the anterior part of the hippocampus. So what you're seeing here, I'm going to take the hippocampus and the fornix out. What you're seeing in this little structure are the hippocampi, one and the second one. And the amygdala will be just on top and more anterior, more forward. Now, the two hippocampi they contribute to what is called the fornix, the white matter of the fornix. The fornix goes around, obviously, just like the corpus callosum. The designers of the model decided to sort of cut it because it becomes very hard to break apart the model, so they've cut it. But this fornix goes around and turns into the mammalia bodies, which are non-existent in this model, unfortunately. But you can't represent everything in a model. It's practically impossible. So here you are, a beautiful representation of where the hippocampus lies in the temporal lobe. And I recommend that you take a little red Sharpie and just draw some amygdalae right here, because that's where they would be, sort of above the hippocampus, above and anterior to the hippocampus, and deep inside the temporal lobe. So what you see here is the temporal lobe. Now, I want to show you something that might be very useful for you to do. When you take this apart, putting it back putting it back is somewhat hard. You have to pay close attention to how the pegs are designed. So this is a technical thing that you should be aware of. So this peg, if you force it, you could break them, but there is only one way for it to go. If you try to do it the other way, it doesn't go. And if you try to force them, they might break. So just be aware. You just have to put them this way. But if you know the neuroanatomy, you'll fully understand why it looks like this. Because you see, this is where the cerebellum would be. And you could see the front of the medulla with its pyramids right here. However, if you take the brainstem and place the little structure that is the hippocampus in its right position, you start seeing the relationship of the hippocampus and the ventricles. See, the hippocampus almost goes around the ventricles, and the hippocampus is adjacent to the inferior horns of the ventricles. Keep that in mind as you study neuroanatomy. Now, let's take the ventricles off, these two lateral ventricles, and remove the insula. And they've represented what's behind the insula in a fantastically interesting way. So this is the insula removed on one side. And what you immediately see is the basal ganglia. What you see here is the caudate, which is the surrounding belt around the putamen. So this is the caudate, and this here in the middle is the putamen. Together, they make the striatum. Differentiate that from the striate cortex. This is the striatum, not the striate cortex, which you will hear about. Now, if you look carefully, you will see that there are striations on this little model to indicate that this is the striatum. Now, if you remove the striatum, now what you would see in a brain is another little structure behind, more medial, more towards the middle, behind the putamen, called the globus pallidus. It's not very clear in this model, but the striatum is this structure, which is the caudate plus the putamen. Now, on the other hand, when you open the other side, when you take out the insula, you see, once again, the putamen, and around it is white matter. And again, they're striated. This white matter is called the internal capsule. So this is a representation of the internal capsule. Now, if you remove the internal capsule as well as a putamen, you will arrive at the thalamus. Deep inside, most medial, is the thalamus. And there are two of the thalami, one here, one here. If you take the medulla off and you separate the thalami, you're going to see a magical part of this model, which is the representation of the two other ventricles, the third ventricle here and the fourth ventricle here. So I'm going to take these, and you see here, this is the third ventricle between the two thalami. This is an aqueduct, something that connects the third and the fourth ventricle, called the cerebral aqueduct. And this is the fourth ventricle. What's really beautiful about this model, again, is they place the aqueduct exactly at the level of the midbrain. So if you put back the two components, what you will observe is the midbrain. Now, when you put the midbrain together, what you will notice is this is the midbrain. It's a very tiny area, but very important area. And from the back, how do I know this is the back? Well, this is where the cerebellum would go, right? These are the peduncles. From the back, you see two bumps. These are the superior and inferior caliculi, very important regions in functions of many animals. Now, what you see here are the optic nerves going into and over what would be the pituitary gland right here. So now we've broken the whole model apart, and your task is to try to put it together. But before you do, I'd like you to be able to identify all the regions I've described to you and see if you can identify further regions. So welcome to my course. I hope you enjoy the playful aspect of the course as well as the serious aspect of the course.